Magnetic fields are everywhere in the universe, from our own planet to the vast reaches of galaxy clusters. On Earth, they protect us from harmful cosmic radiation, guide the migratory paths of animals, and even influence our daily technology. But beyond our planet, magnetic fields stretch across unimaginable distances, shaping the structures of stars, planets, and entire galaxies. Have you ever wondered where these magnetic forces come from? How did they emerge in the vast emptiness of space? For decades, scientists have grappled with this mystery. While we understand that certain processes, like the dynamo effect, can amplify magnetic fields, these mechanisms only work if there's a weak seed field to begin with. This raises an even deeper question: what created those initial seed fields? Recent research has proposed an intriguing new idea, the dust battery hypothesis. This theory suggests that the origins of the universe's magnetic fields may lie in the cosmic dawn, when the first stars and galaxies illuminated the darkness. It's a bold concept that could reshape our understanding of how the cosmos evolved, offering a glimpse into the forces that have shaped everything we know. Stay with us as we explore this revolutionary idea and uncover the cosmic mechanisms that may hold the key to this ancient puzzle. If you find this topic as fascinating as we do, don't forget to like this video, subscribe to the channel, and consider supporting us through the QR code or link in the comments. Your support helps us continue to explore the mysteries of the universe together. The magnetic fields that permeate the universe come in a stunning variety of forms, stretching across scales both familiar and unimaginable. From the comforting pull of Earth's magnetic field to the sprawling fields enveloping entire galaxies, these forces seem to be woven into the fabric of existence. Yet, their origins remain one of the greatest puzzles in astrophysics. To understand where they come from, we must first grasp the complexity of their structures and behaviors. Earth's magnetic field is well known. It protects our atmosphere from harmful solar winds and provides a compass for navigation. On a larger scale, planets like Jupiter generate far stronger magnetic fields, fueled by their unique internal dynamics. Stars, including our Sun, produce magnetic fields that power solar flares and influence planetary systems. But beyond individual celestial bodies, magnetic fields take on a much larger role. The Milky Way, for instance, is enveloped by a magnetic field that spans tens of thousands of light years. It's faint, around 1 million times weaker than Earth's, but its sheer scale makes it a major player in shaping the behavior of cosmic phenomena. Even larger fields exist in galaxy clusters, some stretching millions of light years and influencing the motion of entire galaxies. These immense magnetic structures hint at a universal process, one that has amplified and sustained them over billions of years. For decades, astrophysicists have relied on the dynamo theory to explain these fields. A dynamo is a process where the motion of electrically conducting materials, such as plasma in stars or molten iron in planets, generates and sustains magnetic fields. However, the dynamo requires a starting point, a weak magnetic seed field. And therein lies the deeper mystery: what created these primordial seed fields? The question grows even more complex when we consider the scale of these early magnetic fields. To act as seeds for today's colossal structures, they would have needed to span vast regions of space. But how could such large-scale fields have formed in the early universe, when the first stars and galaxies were just beginning to take shape? This is where traditional explanations fall short, leaving room for new and innovative ideas. The challenge lies in bridging the gap between the small, localized forces that could have existed in the early cosmos and the massive magnetic fields we observe today. Could a subtle process in the infancy of the universe have sparked the creation of these seeds? The dust battery hypothesis offers a compelling answer to this question, suggesting that the interplay of light, dust, and charged particles during the cosmic dawn might hold the key. This theory proposes a mechanism capable of generating those initial magnetic seeds, linking the universe's infancy to the vast and intricate magnetic fields we see now. In the next part, we'll explore how the earliest stars, their light, and the dust they left behind could have sparked this cosmic phenomenon, setting the stage for the magnetic universe we live in today. During the cosmic dawn, the universe was a very different place. It was a time of transition, roughly a few 100 million years after the Big Bang, when the first stars and galaxies began to illuminate the darkness. These stars didn't just light up the cosmos, they played a crucial role in shaping the universe as we know it. Among their many influences, they may have sparked the creation of the universe's first magnetic fields through a process now hypothesized as the dust battery. When the first stars exhausted their fuel and exploded as supernovae, they scattered heavier elements into the surrounding interstellar medium. Over time, these elements clumped together into tiny grains of cosmic dust, the building blocks for the mechanism at the heart of this hypothesis. These dust grains were not inert, they became electrically charged through exposure to radiation and friction with other particles. This seemingly simple property set the stage for something extraordinary. As the second generation of stars ignited, their intense radiation swept through the surrounding gas and dust. The energy from their light didn't just illuminate the dust, it pushed it. Charged dust grains began moving through the interstellar gas, creating weak but extensive electrical currents. Imagine a wire stretched across light years, carrying a faint electrical charge. This movement, though subtle, could have generated the first magnetic fields, tiny but pervasive, spanning vast regions of the young universe. The process wasn't uniform. Variations in radiation intensity and density across the interstellar medium caused the dust to cluster in some areas while dispersing in others. These irregularities created imbalances in the electrical currents, leading to variations in the resulting magnetic fields. Through the laws of electromagnetism, these differences gave rise to large-scale magnetic structures, even if they were initially incredibly weak. These early magnetic fields, created by the dust battery, were faint, billions of times weaker than Earth's magnetic field. Yet, they were enough. Acting as seed fields, they provided a foundation for larger and stronger magnetic fields to emerge. Over billions of years, processes like mixing in turbulent gas clouds and dynamo amplification would build upon these initial seeds, creating the immense magnetic fields we observe today in galaxies and clusters. This hypothesis offers a groundbreaking explanation for the origins of cosmic magnetism. It bridges the gap between the tiny electrical interactions in the early universe and the massive magnetic structures that define it today. However, the theory is still in its infancy and must be rigorously tested. In the next part, we'll examine how these initial fields might have evolved and the astrophysical processes that could have amplified them into the cosmic scale phenomena we observe now. The initial magnetic fields generated by the dust battery hypothesis were incredibly weak, but they laid the groundwork for the vast, powerful magnetic structures we see today. To bridge the gap between these faint seed fields and the colossal fields that span galaxies and galaxy clusters, we must understand the astrophysical processes that amplified them. One of the key mechanisms responsible for this amplification is turbulence within cosmic structures. Early in the universe's history, as gas clouds began to collapse under gravity to form stars and galaxies, they became chaotic and turbulent. This turbulence acted like a cosmic blender, stretching and twisting the magnetic seed fields. These movements increased the strength of the fields, much like how stirring can distribute heat evenly through a liquid. Over time, these turbulent motions amplified the fields, giving them more structure and scale. Another critical process is the cosmic dynamo effect. Dynamo action occurs when electrically conducting materials, like the plasma in stars and the interstellar medium, move in such a way that they generate and sustain magnetic fields. In the early universe, the weak magnetic fields created by the dust battery acted as a seed for the dynamo process. As galaxies rotated and their internal gas swirled, these movements amplified the seed fields into the strong, organized magnetic fields observed today. The role of galaxy clusters is particularly fascinating. In these massive structures, magnetic fields are thought to have been further amplified by the interaction of hot gas and dark matter. Galaxy clusters are some of the largest gravitationally bound objects in the universe, and their turbulent environments provided the perfect conditions for enhancing magnetic fields on enormous scales. Today, the magnetic fields in galaxy clusters span millions of light years and play a crucial role in shaping their evolution. Despite the significant progress in understanding how seed fields can grow, many questions remain. For instance, the exact strength and distribution of the initial seed fields created by the dust battery are still uncertain. Simulations and models are essential to testing this hypothesis. By recreating the conditions of the early universe and including the effects of the dust battery, scientists hope to determine whether this process can fully account for the magnetic fields we observe. Understanding these amplification processes is about more than just solving a cosmic puzzle. Magnetic fields play a vital role in shaping the behavior of galaxies, influencing star formation, gas dynamics, and even the distribution of cosmic rays. By studying their origins and evolution, we gain a deeper insight into the forces that have shaped the universe over billions of years. In the next part, we'll explore how researchers are working to validate the dust battery hypothesis, using simulations and observations to compare predicted magnetic fields with those we see in the cosmos today. The journey to uncover the full story of cosmic magnetism is far from over, but each step brings us closer to understanding the universe's intricate design. Testing the dust battery hypothesis requires ingenuity. Since we can't observe the birth of the universe's magnetic fields directly, researchers turn to simulations to recreate the conditions of the cosmic dawn. By modeling the interactions of light, dust, and gas, scientists can explore whether this mechanism could have generated the weak seed fields necessary for today's massive magnetic structures. These simulations allow for comparisons between predicted and observed magnetic fields in galaxies and galaxy clusters. If the models align with reality, it would be a major step in confirming how cosmic magnetism was born. However, the universe is complex, and questions about the strength, scale, and behavior of these early fields remain. Magnetic fields are silent yet powerful forces that have shaped the universe from its earliest moments. By understanding their origins, we gain a deeper insight into the invisible mechanisms that govern galaxies, stars, and even our own existence. The dust battery hypothesis shows how even the tiniest processes can leave a monumental impact on the cosmos. If the journey into the universe's magnetic mysteries inspired you, consider supporting our channel. Subscribe, like this video, or donate through the QR code or link in the comments to help us uncover more about the forces shaping the cosmos. Together, let's continue exploring the universe's hidden wonders.